Hello friends, my name is Divya Sri Vavi, working as Assistant Professor in the Department of ECE SJBIT. In the previous lecture, I explained about noise in DSP-SC receivers. So the figure of merit in DSP-SC receivers is equal to 1. So in today's lecture, I'll be discussing about the noise in AM receivers. So we'll perform the noise analysis for an amplitude modulation system using an envelope detector. Whereas in DSBSC we have used a product modulator, local oscillator and low pass filter. So here, since it is a AM receiver, we will be using a envelope detector in the receiver. So in a full AM signal, both the sidebands and carrier bands will be transmitted. So it is shown here. S of t is equal to AC into 1 plus Ka into m of t into cos 2 pi fct, where AC into cos 2 pi fct it is the carrier wave, m of t is the message signal, Ka is a constant which determines the percentage modulation. In the expression for the amplitude modulated signal, it is reasonable to assume that the carrier amplitude AC has the same units as the additive noise. The factor Ka, it is then assumed to have the units necessary to make the remainder of the expression dimensionless. As with the DSB-SC receiver, we perform the noise analysis of the AM receiver by first determining the channel noise signal to noise ratio and then the output signal to noise ratio. So this is the usual procedure we are following. The average power of the carrier component in the AM signal, we all know that it is AC square by 2, AC by 2. So when you take the square of it, it will be AC square by 2. So the average power of the information bearing component AC Ka m of t into cos 2 pi fct, here it is AC Ka m of t cos 2 pi fct is 1 by root 2 the whole square. So when you square it, so it will be equal to AC square by 2 plus AC square Ka square P. So in the last video I have shown the relations, it is P by 2. So if you take AC square by 2 as common, it will be 1 plus Ka square P. So the average power of noise is N0 into W. So the channel signal to noise ratio, it is given by AC square into 1 plus Ka square P divided by 2N0, nothing but average power of S of t divided by average power of noise. To evaluate this is the channel signal to noise ratio. Similarly, we need to find the output signal to noise ratio. So this is the conventional AM receiver, where the input to this is a modulated signal S of t and this is the noise signal W of t. We are using a band pass filter. The output of the band pass filter is X of t and we are using an envelope detector since it is a AM demodulation and you have an output signal. So to evaluate this output to signal to noise ratio, we will represent N of t in terms of in phase and quadrature components. So S of t is as usual AC into 1 plus Ka m of t into cos 2 pi fct, and N of t, that is the noise component, we are replacing it with the in phase and quadrature component, that is Ni of t into cos 2 pi fct minus Nq of t into sin 2 pi fct. So we may therefore define the filtered signal x of t, that is through the band pass filter, which will be applied to the envelope detector in the receiver model. So final x of t is this equation. So it is informative to represent the components that comprise the signal x of t by means of phasors. Phasor diagram we need to make use of. So from this phasor diagram, so y of t, that is the resultant, is equal, y of t is equal to envelope of x of t. So in the phasor diagram, if you observe this equation, I am representing in the phasor diagram. In phase with 2 pi fct, you have AC into 1 plus Ka m of t and Ni of t. Sin 2 pi fct is there, so it is taken in perpendicular to cos 2 pi fct, it is sin 2 pi fct. So this is the resultant. X of t is equal to envelope of, y of t is equal to envelope of x of t. So what is envelope of x of t? It is nothing but AC into 1 plus Ka into m of t plus Ni of t the whole square plus Nq of t the whole square to the root. In the sense, we are applying a Pythagoras theorem here. This is a right angle triangle. So x of t whole square is equal to this square plus this square. Nothing but x of t is equal to this square plus this square to the power root. Square root of the whole thing. So the signal y of t, it defines the output of an ideal envelope detector. The phase of x of t is of no interest to us because an ideal envelope detector, it is totally insensitive to variation in phase of x of t. So the expression we are defining here, y of t, it is somewhat complex and it needs to be simplified in some manner in order to permit the derivation of insightful results. Especially we would like to approximate the output y of t as the sum of the message term plus a sum due to the noise. So we should bring this equation into that form. In general, it is very difficult to achieve. However, when the average carrier power is very much larger compared with the average noise power, so that the receiver is operating satisfactorily, then the term AC into 1 plus Ka into m of t, it will be a large value compared to the noise component Ni of t and Nq of t. So at least most of the time. So then we can assume that y of t is equal to AC, I am just multiplying the terms, AC Ka m of t and Ni of t. So this is a pure DC term. This is a present of a pure DC term, or you can call it as a constant term AC, which is in the envelope detector output y of t, and it is due to the demodulation of the transmitted carrier wave. We may ignore this term because it bears no relation whatsoever is the message signal m of t. So there is no relation between that. So next, in case it may be removed simply by means of any blocking capacitors. Thus we can neglect this term AC. So we find that the reminders, that is AC, Ka, m of t and Ni of t. So here we have a scaling factor which is similar to that of the output DSB-SC receiver. So accordingly, the output signal to noise ratio of the AM using the envelope detector, it is average power of the messages AC Ka into m of t. We know this in order to find the power, we'll take the square. It is AC square Ka square into P. So you have this power and the average noise power Ni of T is equal to area under the power spectral density curve from this figure. So here it is 2 times W into N naught. So if you take the ratio of these two, this is what is the SNRO. So this SNRO, it is valid only if the following two conditions are satisfied. The first condition is the average noise power is small compared to the average carrier power at the envelope detector input. The second condition is the amplitude sensitivity Ka is adjusted for a percentage modulation less than or equal to 100%. So keeping this in mind, we have SNRO. Then, in order to find the figure of merit, we'll take the ratio of SNRO by SNRC. SNRO just now we have formulated. SNRC previously we have done. So taking the ratio of it and doing the mathematical operations, you will get the figure of merit as equal to Ka square Am square by 2 divided by 1 plus Ka square Am square by 2. We know that Am square by 2 is nothing but P. So it is Ka square into P divided by 1 plus Ka square into P. If you take like that, that is also fine, or else you can replace Ka into mu by Ka into Am by mu. So that will give you the equation figure of merit is equal to mu square divided by 2 dividing by 1 plus mu square dividing by 2. Just if you alter this, make certain modifications, you will get the equation as figure of merit is equal to mu square divided by 2 plus mu square. So the figure of merit of a DSB-SC receiver, or you can also take SSB receiver which uses the coherent detection, it is always unity. In the syllabus we have only DSB-SC receiver, SSB receiver is not there. So we have observed that figure of merit is unity. The corresponding figure of merit of an AM receiver using the envelope detection, it will be always less than the unity. In other words, what we can say is the noise performance of an AM receiver is always inferior to that of a DSB-SC receiver. Why is this happening? Why is the figure of merit is always less than 1 is? It is due to the wastage of transmitted power which results from transmitting the carrier as a component of the AM wave. So SNRO by SNRC gives us the figure of merit and it will always be less than 1. So here we have a problem to find the figure of merit when we have the modulation depth equal to 100%, 50% and 30%. We know the formula figure of merit is equal to mu square divided by 2 plus mu square. When you substitute mu is equal to 1 for 100%, you will get figure of merit is equal to 0.33. When you substitute mu is equal to 0.5 for 50%, you will get figure of merit is equal to 0.11. When you substitute mu is equal to 0.3, you will get figure of merit is equal to 0.043. This means that other factors being equal, an AM system must transmit 3 times as much average power as a suppressed carrier system in order to achieve the same quality of noise performance. When the figure of merit has been understood properly, now we have another one concept called the threshold effect. When the carrier to noise ratio is small compared with unity, the noise term dominates and the performance of the envelope detector changes completely from that described just now. So in this situation, it is more convenient to represent the narrowband noise N of t in terms of its envelope R of t and phase psi of t as N of t is equal to R of t into cos of 2 pi fct plus psi of t. So the corresponding phasor diagram for the detector input x of t is equal to s of t plus n of t, where we have used the noise as the reference because it is now the dominated term. To the noise phasor R of t, we have added a phasor representing the signal term AC into 1 plus Ka into m of t, with the angle between them being equal to relative phase psi of t, which is between the noise n of t carrier cos 2 pi fct. So it is assumed that carrier to noise ratio, it is low, that the carrier amplitude AC is small compared with the noise envelope R of t, at least most of the time. So then we may neglect the quadrature component of the signal with respect to the noise, and thus directly from the figure where you have seen the phasor diagram, the envelope y of t is given by R of t plus AC into cos psi of t plus AC into Ka into m of t into cos psi of t. This relation reveals that the carrier to noise ratio is low. The detector output has no component which is strictly proportional to the message signal m of t. The last term of the expression y of t, it contains the message signal m of t, which is multiplied by noise in the form of cos psi of t. So we can also recall that the phase psi of t of the narrowband noise m of t, it is uniformly distributed over 2 pi radians. So it follows therefore that we have a complete loss of information in that the detector output does not contain the message signal m of t at all. The loss of a message in an envelope detector that operates at a low carrier to noise ratio, now it is referred to as threshold effect. By threshold, we mean a value of the carrier to noise ratio below which the noise performance of a detector deteriorates much more rapidly than proportionately to the carrier to noise ratio. So it is very important to recognize that every nonlinear detector, example an envelope detector, it exhibits a threshold effect. On the other hand, such an effect, it does not arise in a coherent detector. So this is about the threshold effect in the AM receiver. In general terms, the loss of the message signal in the output of the envelope detector due to the low carrier to noise ratio, we call it as a threshold effect. The detected message signal, it is multiplied by the noise, which is random under the conditions. SNRO is difficult to define and it is meaningless. So this is all about the noise in AM receive. So we'll take up the next topic, that is noise in FM receiver. its noisy model, its phasor diagram, derivation of the SNRO and SNRC, thereby finding the figure of merit of FM receivers in the next video. And also, if we'll elaborate on the phasor diagram, how to draw it, and what are the conclusions we are going to fetch using the phasor diagram. It will be explained in the next video. Thank you.